From the 1960s to the 2000s, physicists at the Stanford Linear Accelerator Center, SLAC, hurled electrons into related particles with as much energy as they could muster. The researchers peered inside subatomic particles, discovered two fundamental particles, and won 3 Nobel Prizes for their efforts. The 2-mile-long accelerator infused electrons with energy, in the peculiar units of particle physics, reaching tens of billions of electron volts, a feat of engineering that stands unrivaled. Now astrophysicists have used another extreme machine to discover a natural electron bazooka that makes SLAC look like a pea shooter. Over the last year or so, a colossal facility high in the mountains of southwest China picked up 2 showers of particles each produced by a single high-energy beam of light, a gamma ray, slamming into the upper atmosphere. Both gamma rays appear to have originated from the Crab Nebula, a sign that the famous supernova remnant harbors the most powerful electron accelerator yet identified. The gamma rays carried a level of energy, millions of billions of electron volts, or a peta-electron volt, PeV, that challenges what theorists thought possible. We were dreaming for decades of detecting a 0.1 peta-electron volt event, says Felix Aaronian, an astrophysicist at the Dublin Institute for Advanced Studies and member of the collaboration that made the detection. No one expected that you would detect 1 PeV gamma rays. A futuristic facility. When natural accelerators like supernovas fire out electrons, the charged particles follow looping and chaotic paths through the universe's many magnetic fields in a way that hides where they came from. But when one such particle plows into omnipresent microwaves soon after being launched, the collision releases a gamma-ray flash that flies straight. Looking for the particle showers produced by these intergalactic emissaries is one mission of the Large High-Altitude Air Shower Observatory, LHASO. LHASO sits nearly 3 miles above sea level on Hazy Mountain in China's Sichuan province. There it looks for cascades of thousands of electrons and other particles, debris unleashed by cosmic rays or gamma rays crashing into Earth's atmosphere. The facility features multiple types of detectors spanning more than a square kilometer of combined area both above and below ground, making it 10 times larger than the previous leading instrument. The more than 5,000 detectors above ground watch for the ensemble of particles raining down after both cosmic ray strikes and gamma ray strikes, while the more than 1,000 underground detectors sense only muons. These hefty electron cousins appear often during cosmic ray showers, but less frequently during gamma ray showers, which lets researchers eliminate them and focus only on gamma ray hits with a precision no other Earth-based instrument can match. People call it a facility from the future operating now, Aaronian says. 2 blinding gamma rays. Until recently, LHASO has been under construction. And one of the first things astronomers often do while tuning up a new telescope is to observe the Crab Nebula, the remnants of a supernova spotted by Chinese astronomers in 1054, and one of the most thoroughly studied objects in the sky. It's the superstar in the sky, Aaronian says. Sometimes we call it the standard candle. The Crab Nebula passes above LHASO for about 7 hours each day, so as the collaboration was ramping up operations, scientists working at the facility spent thousands of hours watching it. All seemed as it should, except for 2 surprises. Last year on January 11th, nearly 5,000 incoming particles lit up around 400 surface detectors, with just a few muons making it to the sensors underground, what you might expect to cascade down from a 0.9 PeV gamma ray hitting the atmosphere. This year, on January 4th, the Crab Nebula flared again, this time with an even mightier gamma ray registering about 1.1 PeV. At the time, the photon was the highest energy light ray ever recorded on Earth. LHASO has since recorded a 1.4 PeV gamma ray from an entirely different type of source. The collaboration described their findings yesterday in the journal Science. Records aside, what really intrigues the researchers isn't the light rays themselves, as much as the speedy electrons that initially sent the flash of light hurtling straight toward Earth, and the monstrous cosmic hardware capable of accelerating the electrons to such unheard-of energies. 1 PeV is a real surprise, Aaronian says. We knew that Crab is a super-efficient machine for converting energy and for accelerating particles. But now we see even super is maybe a bit modest. A highly efficient contraption. So how is the Crab Nebula spitting out such zippy electrons? Astrophysicists have a rough idea. At the center of the cloud lies a pulsar, an 18-mile-wide neutron star that whirls around wildly about 30 times each second. From this spinning stellar husk, a wind of electrons and their antimatter partners blows outwards at a respectable percentage of the speed of light. Eventually, this electron gale slams into the surrounding dust cloud, sending out a shockwave of electrons and other particles, some of which would emit gamma-ray photons of the sort that LHASO picked up. The challenge, according to Aaronian, is to understand the last stage, How the wind slings electrons with enough oomph to make a 1 PeV gamma ray. A powerful local magnetic field must be involved to get the electrons hustling, but more powerful magnetic fields also cause electrons to release more particles as they pass through, causing a sort of drag process that engineers have struggled to minimize while building earthbound accelerators like SLAC. Nevertheless, the Crab pulsar somehow managed to hand almost every smidgen of energy in its electron wind off to the 2 electrons that sent gamma rays toward LHAASO last year. Based on LHAASO's observations, the pulsar likely fires off enough PeV electrons each second that these particles alone carry away as much energy as our entire Sun radiates in all wavelengths. Astrophysicists are stumped as to how so much energy gets into the zippiest electrons. It's at the margin of reality, Aronian says. It cannot be simple shock acceleration. It should be something special. LHAASO spotted these 2 ultra-high energy light rays, along with a bunch of only slightly less peppy photons, during its construction, while working at roughly half of its potential. Now that the facility has reached full sensitivity, the collaboration looks forward to at least a decade of collecting more details about what the Crab Nebula is capable of. In a few years we'll know a lot, and I think surprises could come, Aronian says.